Welcome back, everyone, to the GOCC this semester. So today we have Aditya Khanna speaking about proving two matrices are mutually inverse using pictures. Before we get started, let's just remember our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So, Aditya, whenever you're ready.
Thank you so much. Thanks to the organizers for inviting me to give this talk. It is kind of funny. I did organize the GOCC for a while, but I've never given a GOCC talk. So, hey, inaugural talk. Uh, this is the title. I want to prove two matrices are mutually inverse, and we will do this using pictures. I gave a short 10-minute version at JMM, and so this is like the full uncut and uncensored version. So let's get started. We will start with matrices, right? A matrix M, we have a matrix M, and this is basically a map between two vector spaces, right? And so what we could really think of, this is fundamentally a map on the basis elements of V, and it sends them to somehow the basis elements of W, right? So this is what we think about as matrices. One second. Hello? Yeah. Oh, definitely. No, that completely makes sense. Yeah, sure. I can do that. Yeah, cool. Uh, so I just received information because this is a combinatorics seminar. I need to restrict our attention to combinatorics. So let's start again. We start with combinatorial matrices. A matrix is called combinatorial if all of its entries can be computed as a sum over some objects. What does that mean? If I have this entry -1, so it is in some row and some column, then I can compute this -1, say as the sum over three objects, where in this case, one object has some weight associated to it called -2, and the other two objects have weights half. So if you add all of these up, you get -1. So this is the definition of combinatorial in our case. The most famous example of this, these are called Pascal matrices. You have seen them. Uh, you have this 5 by 5 matrix. And for example, if I look at this entry 6, this is given by taking the column index and choosing it with the row index. So 4 choose 2 gives you 6. This is the algebraic way to count it, but algebraic way to compute it. But what this is fundamentally doing, it is counting some objects, right? These are the 6 objects that you get. And what is a single object? It is a way to put two boxes, so the row index, in 4 boxes. So 2 balls in 4 boxes, and all of the ways, that's what this is counting. And so this is a combinatorial matrix because it's counting something. Furthermore, matrices are maps between bases. So if you consider these two bases of the polynomial ring, the very famous binomial theorem tells us that these coefficients are actually the entries of this matrix. So these are the two ways to look at matrices, one as maps and other as counting objects, and this is the interplay that we'll be looking at throughout this talk. But I don't really care about Pascal matrices. The thing I care about are called Kostka matrices. But in order to even understand what these Kostka matrices are, we need to know what the rows are indexing and what the columns are indexing. So we need a little bit of background. And people in this audience might be aware, but I will still go through all of the definitions. Let's start with compositions. A composition is basically how to break up a number into its additive constituents. So it's a list of numbers that sums up to n, that we call it a composition n. So 3, 1, 2, 3 is a composition of 9 because 3 plus 1 plus 2 plus 3 is 9. And we will draw these compositions out using these things called diagrams. And a diagram basically places 3 boxes in the top row, 1 box in the second row, 2 boxes in the third row, and 3 boxes in the fourth row. This is how we'll represent. Special case of composition, they are called partitions. And partition is when I arrange these numbers in a weakly decreasing fashion, so descending, and they can be equal at some point. Whenever I say composition, whenever I say partition in this talk, I want you to keep both of these notions in your head. Uh, the diagrammatic notion as well as the list, we will jump between these quite often. Because we now have boxes, we of course want to fill them. So in this case, lambda will be a partition, beta will be a composition. Almost throughout this talk, lambda, mu, and gamma will be partitions, and beta will be a composition. So what I'm going to do, I'm going to fill it according to some rules. And the rule here is this. When I go from left to right along a row, the entries either increase or they stay the same. But when I go down a column, they strictly increase. So in the second row, I increase going from left to right, or I stay constant. So it's 2, 2, 2, 4, 4. But down the columns, you'll see that the increases are strict. That's where the semi part comes in. The semi means, oh, the entries in the row can also be equal. So this is a way to do a filling, and the semi-standard filling will be what we'll be focusing on. In this case, what are we filling? We are filling this particular shape. And what is this diagram? It has 6 boxes in the top, 5 in the second row, 5 in the third row, 3 in the fourth row, and 1 in the last row. And so this is the shape, the diagram. And now let's see how we are filling this diagram. Right, so we have seen what we are filling. Now let's see how we are filling it. We will record that using composition. So I'll see first how many ones appear. There are 3 ones appearing, so I'll put a 3. Then there are 5 twos appearing, so I'll put a 5. There are 3 threes, 4 fours, 2 fives, and 3 sixes. And now this is telling me how to fill this shape. So we'll call this a semi-standard Young tableau, shortened to SSYT throughout this talk. The shape is lambda. What are we filling? Content is beta, and content will be a composition. So the content tells you how to fill something. This is a good time to stop for questions. Are there any questions about any of the definitions? I will wait a second. Okay, going once, going twice. Cool, let's move on. So back to matrices, what is a Kostka matrix doing? It is counting these semi-standard Young tableau. For example, if I look at this particular entry, this is a 2. I look at the row and I look at the column. The row describes the shape, the column describes the content. So I need to fill the shape 3, 2, 3 rows on top, 2 on the bottom with this particular content, which says fill it with 2 ones, fill it with 1, 2, and fill it with 2 threes. And this is exactly what you get. 2 ones, 1, 2, and 2 threes. Another example, this 3 here corresponds to the shape 3, 2. So 3 rows and 2 rows in the bottom again. And the content 2, 1, 1. So 2 ones, 1, 2, 1, 3, and 1, 4. And now we get 3 of them. That's what the 3 in the Kostka matrix means. So this Kostka matrix is actually recording all of the semi-standard Young tableau of a given shape and content. And in general, we will denote it using this k lambda comma beta. I will either use k parentheses lambda comma beta or k subscript lambda comma beta, depending on how much space I have on the screen. And we'll call these Kostka numbers. So, oh yeah, I did say matrices were maps, but that means the Kostka matrix should be mapping between something, right? Now let's see what's happening. This brings us to the main algebraic object of my study. These are called symmetric functions. A symmetric polynomial is a multivariable polynomial such that if I swap any 2 variables, the polynomial does not change. So if I swap x and y and compare it to the original polynomial, I see I have a y squared xc here, I have a y squared xc here, I have a yx squared z here, I have a yx squared z here, I have a xyz squared here, and I have a yxz squared here. everything matches up. So this polynomial did not change. Symmetric functions are basically the same thing, but in infinitely many variables. And when I say a symmetric function of a given degree, so in this case, you see that degree is 4. There's degree 1, degree 2, and degree 1. So this has degree 4. So symmetric functions of degree n, if I take all of them together, they form a vector space. It's a vector space. That's good. That means there might be matrices lying in the background. So let's consider an example of symmetric functions. We call them h subscript n, hn. This is the sum of all monomials of degree n. How do you construct it? Well, h3, how do you construct monomials of 3? Well, a cubic is a monomial, so x1 cubed, x2 cubed, x3 cubed. Another way to do is quadratic times linear, so it's x1 squared, x2, x1 squared, x3, and so on. Or you can consider 3 linears together, so you get something of degree 3. And why is it symmetric? Well, if I swap any variables, the degree in this particular case will not change. So a term here will just swap to a term within the sum itself. So this is symmetric. And I can extend this definition. So if I take a composition beta, I can define h beta to be a product of these h's which are indexed by the entries of the composition. So I have h subscript 4314. Well, that is just h4 times h3 times h1 times h4. Product of symmetric functions is also a symmetric function. So what we are looking at right now is indeed a symmetric function. And an important thing is that if I take all of these h betas for compositions beta, then this is a spanning set for my symmetric functions. So this is the definition of h. We'll keep this on the side and move on to another sort of symmetric function, probably the most famous symmetric functions of all time. So how do we construct these? We take a semi-standard Young tableau. For example, this example that we are using the whole time. And then I look at its shape and content. This is what we computed earlier. And all I do is I take the ith entry of the content and raise it to the power of xi. So here I have the second entry being 5, so x2 will be raised to the power 5. That's the content monomial. Every semi-standard Young tableau has a content monomial. So what I can do is I can give you a fixed shape. So I give you just the boxes, ask you to fill it in all possible ways, find the content monomials of those semi-standard Young tableau, and then sum all over them. This ends up being a symmetric function. The next slide we'll do an example. But there is a small caveat that instead of filling compositions consecutively, like first I fill the ones, then the twos, then the threes, then the fours, I'm allowed to skip over some labels. So I might fill the ones, then I might fill twos, then I might not fill any threes. So in the third position, I will have a 0 in the content. So I'm allowed to have zeros in my content so as to skip over some labels. So yeah, thank you for reminding me for this caveat, friend. So now let's look at an example for 3, 2. I have this particular shape. I fill it with 3 ones and 2 twos, so x1 cubed, x2 squared. That's what we get. And now there's an example where we skip a label. So I have 3 ones, which gives me the x1 cubed, but I have 2 threes. So I've skipped a 2, so technically this is the composition 302. But we are going to ignore that. This has 2 ones, 1, 2, and 2 threes, giving you 2 ones, x2 to the 1, and x3 squared. Similarly, we have this example where x1 times x2 squared times x3 times x4, or all of them can be different. So you have this 5 different variables altogether. And just take all of the ways of filling, and this will give you your symmetric function. The proof of this function being symmetric is a little bit involved, so we're not going to cover. So just take my word on this. So what are these Kostka numbers now? We saw what they were combinatorially. They were counting semi-standard Young tableau. But in this case, the S lambdas, if you take for all partitions lambda, these form a basis of symmetric functions of degree n. So not just a spanning set like the H's did, a full-on through and through basis. And what we can do is we can convert between H beta for a composition beta and express that, because it's a symmetric function, right? We can express that in this particular vector space basis, and we get the coefficients, Kostka numbers. There's also a way to understand this using non-commutative symmetric functions, which make this more Bayesian-like. But right now, spanning set is being expressed in terms of a basis. And that's why all of the matrices that you'll see will be rectangular. This is a good time to stop. Questions? I'll wait a couple seconds. T minus 3, T minus 2, T minus 1. Okay, we have left off. We will move on if there are no questions. You're also very welcome to stop me in the middle of a talk anytime you have a question on a particular slide. So these constructions that we have done till now are pretty important, but before we actually move on, I just want to look at this whole thing that we are talking about. Uh, Actually, we'll talk about this a little bit later. Let's skip about that. So what are we doing, right? We want to understand this interplay between these bases that are going around and also the combinatorics that's happening. One thing that we notice about our Kostka matrix, right? Remember this example, we had 2 here and it was counting these 2 tableaux. This is a fun observation that if you remove the 2 largest entries, so if I remove the 3's, what do I get? I get these 2 guys. One has shape 3, one has shape 2, 1. And now if I look at the Kostka matrix corresponding to n equal to 3, then I see that the shape 3 and content 2, 1 has exactly the entry 1. So that's this tableau. Shape 2, 1 and content 2, 1 and has the entry 1, which is exactly this tableau. And what do you know? 1 plus 1 is equal to 2. Another example. These were the 3 things that we saw. I'm now again going to remove the largest entry. So 4 will get removed, giving us these guys. And now you see that the shape 3, 1 and content 2, 1, 1 has an entry 2, which corresponds to these 2 tableaux. Shape 2, 2 and 2, 1, 1 has the entry 1 corresponding to this tableau. And it's not hard to notice, 2 plus 1 is 3. And this is the fundamental recursion that we will build our whole proof on. So what we are doing is I'm taking a projection in some sense of the composition. So in this particular case, you saw that we started with the content 2, 1, 2, and I removed the last part. Similarly, I started with the content 2, 1, and I removed the last part. So in general, we define this to be the projection of the composition, beta star, and we remove the last entry. So if I have 2, 1, 2, 4, I can remove the last entry to get 2, 1, 2. And what we noticed, this is what it was doing, is that to figure out the entry lambda comma beta in the Kostka matrix, I find the entries in the projection corresponding to the composition, which is the projection, and then I find out some rows which add up to that. And these are exactly the rows that correspond to the partitions, which you obtain after removing those largest cells. So this is the basic Kostka recursion. And honestly, this is a very general idea. Multiple matrices that you will encounter in symmetric functions and combinatorics will show this behavior. So what do we have? If I want to find for a general matrix A the entry lambda comma beta, then there is a family which shows this sort of recursion where if you look at the column corresponding to the projection beta star, there are some entries which, when put together, contribute and make this entry happen. So in our previous case, we saw that they were adding up, but that's not always the case. You could also have a linear combination. So if I want to figure out this entry in the bigger matrix, I actually look at the projection column in the smaller matrix, look at those entries, take a linear combination, and this gives me the entry. So whenever matrices show this sort of recursion, our theorem that I will soon talk about will apply. So this is the setup that we are dealing with. What does this look like on an object level? When do matrices show this behavior? So what did we do? We took this tableau and we removed the largest entry. And this actually gives us a recipe to construct these objects iteratively. So in this particular case, I have these semi-standard Young tableau and I've shaded all the cells with the same filling. Uh, yes. Is there a question? Okay. Uh, so in this particular case, if I have semi-standard Young tableau and I shade the cells corresponding to the similar entries, for people who haven't seen this before, what do you notice about the highlighted cells? For people who have seen this before, here's a GIF of a red panda. Audience participation, if you haven't seen this before. What do you notice about the cells?
They're kind of like moving down and to the right, generally
They are
speaking.
moving, that is good. They're moving down into the right. But if I look at a particular diagram and I just look at these shaded cells, what do I see?
There's no
So
more than one in a column. I mean, I guess that
perfect.
follows from definition, sort of, but
Yeah. No, that is exactly it. Uh, there are no two cells in the same column, and that follows from how we define the semi-standard tableau. But we are now looking at an alternate way to construct it. So we will call these horizontal strips, and horizontal strips are exactly as Alex said. Two of them do not share the same column. And this is a very important point that Tableau, almost all the time, Tableau are recording how a given diagram is constructed. So they once tell you to do something in step one, the twos tell you to add these cells in step two, the threes tell you to add these cells in step three, and so on. So by adding these cells, horizontal strips, step by step, I am constructing my final diagram. And how am I doing it? These numbers are telling me how to do it. So this idea of a tableau being how to add something will be important. So semi-standard Young tableau are built using horizontal strips. So that's the recursive combinatorial description of semi-standard Young tableau. Now let's move our attention to the inverse Kostka matrix. In this case, this is my Kostka matrix that I'm calling the Kostka matrix for this talk, and I multiply it with this particular right inverse, and I get the identity matrix. For this talk, I will call this the inverse Kostka matrix. This is not an inverse, of course, because this is a rectangular matrix. But what we notice is that this matrix only has ones, minus ones, and zeros. And that is pretty nice. We will soon talk about what these ones and minus ones mean, but this is pretty good for us. And this justifies why this was a rectangular matrix in the first place. If you look at these two columns are just redundant. Like actually, these three columns are just the copies of each other. And you will see the indices are also anagrams of each other. So there is so much redundancy built into the Kostka matrix, and that is actually giving us this really nice behavior for its rectangular right inverse. And so now that we have this matrix, let's talk about how to compute it combinatorially. For that, we need a concept called ribbons. So I'm going to shade something, and a ribbon is something that snakes along the boundary of the diagram. Formally, this is something that does not have a 2 by 2 square in it, but it is something that goes along the border of your diagram. So I've shaded the border, and it's a subset of this particular border. That's why you will also see them being called rim hooks or border strips. In this talk, we will call them ribbons or rim hooks. So this is what a ribbon is. It goes like this. A special ribbon is something that starts in the leftmost column. What I mean by that is the bottom left cell of my ribbon is in the first column. So you can sort of see, like, if it's going from left to right, it is starting in the left side. Now I have these diagrams, and I'm going to shade all of the special ribbons in it. And you can see that all of them are starting in the leftmost column. We can associate a sign to each ribbon. So if I have, for example, this is a better example. If I have a ribbon occupying 3 rows, then I do 3 minus 1, and minus 1 squared is plus 1. So this ribbon has sign plus 1. Similarly, this ribbon is occupying 6 rows. 6 minus 1 is 5, minus 1 to the power 5 is negative 1. So this has sign negative 1. And by same way, I calculated for everyone. And you can see that these are the signs that you get. Similarly, so we talked about horizontal strips, right? And horizontal strips for building up semi-standard Young tableau. Now I have a new collection of cells that I can use as my ingredient to make new tableau. And these are unsurprisingly special ribbon tableau. We will now do the same thing. A tableau tells us how to add things. So in the first step, I'll add this particular special ribbon. Then I'll add this special ribbon. And then I'll add this special ribbon. Then I'll add this special ribbon according to my special ribbon tableau and keeping the account of signs at every step. Now, if I look at the sign of the whole thing, that is actually a product of the signs I just got. If you multiply them, you'll get negative 1. I believe so. Yeah. So you get negative 1 when you multiply them. And just to point out, this is something of shape 4, 4, 3, 3, 3, 3, 1, and it has content 6, 5, 8, 5, understood similarly as how many 1s are there, how many 2s are there, how many 3s, how many 4s, or equivalently, at each step, what is the size of the special ribbon I'm adding? I'm adding a 6, special ribbon of size 6, special ribbon of size 5, 8, and 5. So now we have an iterative construction of special ribbon tableau. So let's go back to our matrices. I'm not going to prove this, but just trust me on this. There exists at most one special ribbon tableau of a given shape and content. So if I give you a shape and tell you to give me a way to construct this using special ribbon tableau, and I fix the content, at each step you can either add a special ribbon tableau, a special ribbon, or you cannot. And if you can always add, then it works. Great, there is one of that. But if you cannot, it just doesn't work. So there is at most one, it either works or it doesn't work. And this is exactly how we will compute this matrix. So if you look at this minus 1, it has exactly one object of sign minus 1. So it has exactly one special ribbon tableau of size minus 1. The 0 here is not coming from two things, say plus 1 and minus 1 cancelling out. In this case, the 0 means there is no object. Similarly, this 1 is not coming from multiple objects. It's coming from one single shape. And that is where the redundancy of this Kostka matrix is very important. Because we are indexing by compositions, we get this really nice behavior. And of course, if I ask you to prove this identity, you can just multiply them out. Right? There's nothing special to that. But we spent so long talking about pictures. Is there a proof using pictures? So I'm going to checkpoint on the cliffhanger. Are there any questions? We have defined a bunch of terms. This is also a reminder for you to hydrate. Okay, we have discussed two main matrices, the Kostka inverse, and we have seen what their combinatorial interpretations are. Not only that, we have seen how to build those combinatorial interpretations recursively. So this is where we are right now. Before I present what we did, I want to talk about how other people have worked on it. So I'll denote by this particular straight K to be the square Kostka matrix. So you remove all the redundancies, you get a nice square matrix indexed by partitions. And people have studied how K times K inverse is equal to I. So this is also the inverse square. So Agassi, and Remel have a really nice bijection, but their bijection is not free of arbitrary choices. They define this special thing where they have to like swap entries, and they use partitions as their fundamental object, and that requires a bit of reordering, which makes proofs complicated. Uh, Another thing of interest is that K inverse is I, but proving K inverse K equal to I is a different question combinatorially. We can talk about why these two are different cases. But a lot of work has been done with that. We will prove this. So K inverse is what we'll prove in this talk. We won't talk about K inverse K. And also there is very recent work by Allen, Solano, and Mason. And they use Garcia-Millen involution. And they do use compositions. They use like a non-commutative, which is fundamentally what we're also doing. But their proof actually relies on some arbitrary choices, while we claim that ours is canonical. So it's time for building up to the punchline. We have a theorem. So Kn is now the Kostka matrix, the one we have been talking about, the rectangular version, not the square version. And so rows are indexed by partitions, columns are indexed by compositions. You have Kn times Kn inverse. This is also the rectangular inverse Kostka matrix, and this is equal to the identity. And we have an equivalent condition for this, which is this. I start with a partition and I remove a horizontal strip to give me an intermediate partition. Then I add a special ribbon. I will, of course, show a bunch of examples so it will become clear what I'm doing, but this is the idea. That I'll start with a partition, I'll remove something, which is the horizontal strip, then I'll add a special ribbon on it, and then I will see what is the sign of this process. If the total sign is 0 for mu not equal to lambda, and it should be 1 for mu equal to lambda, this is exactly the condition that the off-diagonal entries of an identity matrix are 0, while the diagonal entries are 1. So we'll be removing something and adding something and looking at signs. And turns out that is enough to completely prove this particular thing. So let's look at the case when mu is equal to lambda. So I start with a shape, I end with the same shape, and I remove a horizontal strip, and I add a special ribbon. Well, if I remove something and add something, and I get to the same shape, the only way that is possible if I remove and add the same thing. So I need a horizontal strip that is also a special ribbon, but we saw like ribbons really want to climb up a column, but horizontal strips do not want to be in a column. What is the resolution here? What is something that is both a horizontal strip and a special ribbon? Audience participation.
Is it if it's just at the bottom, like the first special ribbon?
Yeah, that is exactly it. Thank you. So it is something that is, not going up. If you just say, oh, don't go up, then that's enough. And so a single row, as Alex said, is exactly a horizontal strip as well as a special ribbon. So I start with a partition shape. I nix the bottom, giving me an intermediary shape, and then I add it back. And this has the sign. So because it only occupies one row, remember that ribbons have sign row minus 1. So this has sign 1 minus 1 to the power 1 minus 1, which is 1. And this is exactly what the theorem wanted. When mu equal to lambda, we should get a total sign of 1. I want to point out that removing a horizontal strip has no sign. The process has sign just 1. So it doesn't contribute a minus or anything. Now let's look at the more exciting case where the starting and final partitions are not the same. So I remove a horizontal strip, I add a special ribbon. What happens? Well, I start with this. I remove some horizontal strips and I add a special ribbon. This is my mu, this is my lambda. Again, how many other ways do you think there are to go from this shape to this shape by using this removal and addition process? I don't expect you to know this because we proved this in the paper, but what do you guess?
Is there only going to be like at most one special ribbon of a given size? So
Yeah,
is there
but
like one way to do it?
right. So, but I could remove a horizontal strip of a different size.
Oh, okay.
Yeah. I mean, yeah. So, spoilers, there's exactly one more way of doing it, which is the main fundamental essence behind the canonicalness that we'll see later. So, how do you figure out what this way is? Uh, Before that, we need a little bit of background. I have this special ribbon. I will call this the head, which is the top right cell. And we will describe an involution, which basically says this. I'll show examples. So the head of S, if it intersects with my horizontal strip, I push the special rim hook down. If it doesn't intersect, I push it up. What does that mean? So this is the setup that we currently have. And now let's look at this. This is the head of my special ribbon. It is 1, 2, 3, 4, 5 in the second row. And then if I look at this, this is 4 in the second row. And that means they don't intersect. So now I push my special rim hook up and I get this new one. And now I work my way backwards, getting the intermediary shape and then getting a corresponding horizontal strip. And what you will notice is that this occupies 2 rows, so it has sign -1. This occupies 3 rows, it has sign +1, -1, +1, I believe, is 0. And so this is exactly what the theorem wanted. Looking at another example has never hurt anybody in the history of mankind, so we'll look at another example. I start with a partition mu, end with a partition lambda. By removing horizontal strips, getting this intermediary shape, and ending here. Now we will see that the head actually, this is the fourth, right? So it does intersect with my horizontal strip. If it does, I'm in the first case. And now I will need to push my rim hook down a row, and this is what I get. Then I get an intermediary shape, and then I pull back once more. And this process is now paired with a process. So the way you should think about this is pairing up processes. And again, same calculation. The up one has sign -1. Yeah. And the bottom one has sign +1. -1 +1 is 0. So this indeed works. And what we show in the paper is a general case, right? I'm showing through examples, but we prove that this will always work. And this is actually an involution. So we have proved Kn times Kn inverse is equal to I. This is a general thing, and the generally what you can show is if I have two matrices An times Bn such that their product is identity, and they're indexed by some objects. So the columns are always indexed by compositions. That is one restriction that we have. while the rows are indexed by basically any objects, mostly partitions. What you do is you start with mu, you remove a lot of strips of size L, you remove a strip of size L according to AN, you get some intermediary objects. So in the previous case, we were getting two intermediary objects, but you could get as many as you want. And then I add a strip. This is more abstract than, just removing cells because your objects could look different, but this is the main idea. I start with a bigger object, I undo the recursion that comes from A, then I do the recursion that comes from B, and I get lambda. And all of these processes, so this removal process has some sign associated to it, this addition process has some sign associated to it, and the product of these signs is the product of this whole process. And if I do this for all intermediate objects, so each process can be associated to an intermediate object. If I do this for all of them, I should get a 0 on the off diagonals and 1 on the diagonals. So this is the very general idea. And that's why this process is so strong, because not only does it work for the Kostka case, but a variety of cases. If I have time at the end, I might showcase a few. Okay, actually time for the punchline. We saw that this is some weird equivalent condition, right? I'm removing or adding some stuff, but on the level of objects, this is not what's happening. So what is actually happening? What is the bijection that proves it? Well, if I multiply two matrices, if row lambda and column mu, this is how you multiply matrices, right? You go iterate in the columns and you iterate in the rows of the other. So A lambda beta times B beta mu. And this is the lambda comma mu entry. But the entries of, because these two are both combinatorial matrices, A can actually be understood as a sum over some objects. And this entry B can be understood as sum over some other objects. So instead of just looking at this as a sum over products of numbers, we will imagine this as a sum over pairs of objects. So in this case, think of the product of the Kostka matrix and the inverse Kostka matrix as a pairs of semi-standard Young tableau and a special ribbon tableau. So if I have that, then again, because this is equal to the identity, we'll need this condition to happen. And so combinatorial proof actually is doing this thing, where it's taking a pair, it's combining how these pairs will cancel out. So what we show is a sign reversing involution. This is not always a sign reversing involution, but for the Kostka case, it's a sign reversing involution, which to me is like the most fundamental combinatorial essence of most things. What it does is it takes a pair, so assume a semi-standard Young tableau and a special ribbon tableau. It can either be a fixed point, or it can generate a new pair that has a opposite sign. So actually, let's look at this in motion. So if lambda is equal to mu, we saw that the only special ribbons only special ribbons that are also horizontal strips are single rows. So if something is a semi-standard Young tableau and also a special ribbon tableau, in this case, this is the only possible object when your shape is the same. And you will see that this has sign 1 because each filling only occupies one row. So the sign of this pair is 1, and that is exactly the lambda equal to mu, diagonal entries are all 1. What happens for off-diagonal entries? You start with a pair of semi-standard Young tableau and a special ribbon tableau. I will strip away the largest entry. Then I'll strip away the largest entry again until I'm left with something that looks like that fixed point. So I have 1s in the first row and 2s in the second row. And you will see that this very nicely resembles the exact involution that we were talking about. So the colored things are actually this pair on the top. So what I'll do, I'll take this on the top and convert it into the bottom guy. And so I apply this involution now, and then I restore everything else the way it was. And this pair here has an opposite sign to this pair here. The reason we say it's canonical is because at this point, there is exactly one option for you. We are not making any choices about which labels to switch around. After you do this, the stripping apart is given by the recursions. So we have to do that. We end up here, we apply the involution, and we restore everything. So this pair is canceling out with this pair. So we have proved K times K inverse without explicitly ever multiplying out the matrices. Let's see, in the last 2-ish minutes, I will rapid fire go through what else we do in the paper. We look at these things called ribbon tableau, which are basically special ribbon tableau, but the ribbons are not special anymore. If I remove a ribbon and I add a ribbon, that's the same as removing, that maps to another pair which cancels it out. So this is -1 plus 1. Same idea, this gives you 0. This proves that the characters of a symmetric group are orthogonal, if you care about that. Then we also do another application for matrices like this. I have not indexed this, but so this is indexed by sets of size 3, subsets of 3. So if I have a set belonging to another set, so if S is contained in T, I put 1. If S is not contained in T, I put 0. And the inverse of this has the same locations of the non-zero entries, but the signs are slightly different. And we prove them using these things called composition diagrams. I do not want to focus on what the specifics are, but notice that there is some removal happening, then some addition happening, some removal happening, some addition happening on diagrams. And there's a -1, there's a +1, things are canceling out. So fundamentally, this is the same idea. And the cool thing is this is actually the diagram proof of inclusion exclusion. And the final thing that I want to point out is I will not define brick tabloids, but we also prove stuff for brick tabloids. But before you leave this talk, I don't want you to give you a false impression. It's not always an involution. If you start from an object and end on an object, you could have intermediary objects. For example, in this case, 3 objects come together and cancel out. So it's not always that there is a unique other object that it cancels out with. And so this is the sort of stuff we show in our paper. There is an archive link here in case you want to scan that. We do a lot of stuff because of how much we use compositions. We can show a lot of things about quasi-symmetric and non-commutative symmetric functions also. And our paper gives new bijections, which are more concise and canonical because of the involution that we get. And another really interesting thing is that this doesn't need to apply to only matrices coming from symmetric functions. Other matrices which are recursive, such as the Hadamard matrix, can also be used in this framework. Finally, thank you for listening. This is the link to the paper. And if you can, please fill out a feedback form for this talk. Peli and I were wondering if we could ask people to start filling out feedback forms. You're also welcome to take this feedback form and put it in your talk at the end. We believe that giving each other honest feedback and constructive criticism will be useful to the community. So thank you.
Thank you very much, Aditya, for such a wonderful talk. We'll open it up for questions. So does anyone have any questions? I would maybe have a question. So how can we think about general Kostka matrix multiplication? So in the case that we're not like working with inverses in the identity matrix, can we use the same kind of principle, some kind of combinatorial operation on these tableau? just given general matrices, assuming the dimensions are compatible?
So general matrices, not Kostka matrices.
Um, yes, Kostka
Or
matrices.
so what's the question again?
So I guess if we have like two Kostka matrices and their dimensions are such
Hmm.
that we could matrix multiply,
Just
is
such the
there maybe a
dimensions
way we
are
can
like.
interpret the entries
Uh,
of the product?
so the entries of a product, whenever you can multiply things, will always come down to being pairs of objects. For Kostka matrices, the dimensions are always for square, it's partition times partition, or partitions times compositions.
Mhm.
So in this case, you can't multiply that, but in general, every multiplication of matrices which are combinatorial in nature is the sum over pairs of objects.
Mhm. Okay, so we can't interpret like an entry in the product as like some number of fillings of some larger tableau of like a, you know, augmented shape and content.
Hmm. Yeah, so if you have two tableau in a pair, you could maybe define a bijection on the pair that maps it to a single tableau. For semi-standard and tableau, I think you can do that. Uh, that is probably how the Littlewood-Richardson rule works. Uh, you put them together and then you can do some sort of thing that gives you a bijection. Uh, but I don't know how general that is. If you can imagine that as a singular entity.
Thank you.
Mhm.
Any more questions for Aditya?
I had a question. So for you're saying that the columns of your matrix always have to be compositions, but the rows can be some other combinatorial
Mhm.
objects.
Yeah.
Do you have any examples that aren't partitions? Or I guess are they always like partition like?
Are they always partition like? Yeah, that seems to be the case that we're always looking at. Uh, so yeah, so the two examples that we have in our paper are always indexed by partitions and are or compositions. So no. Right now we don't have any examples of things that are where the rows are not indexed by partitions. Considering how I mostly work with symmetric functions, I just also only know examples of matrices that are indexed by partitions nicely. Uh, One thing that I showed is that compositions are in bijections with subsets, so you can do something over there, but that is still in bijection with compositions. So if you ever see
Thanks.
anything in the wild, do let me know.
Maybe one last quick question. So I didn't get a close look at the examples, the like of Kostka matrices that you presented, but it's not known in general that the Kostka matrix is like totally non-negative or something. Or
Uh, like the rectangular ones?
yeah,
Is it
I'm
a
just curious if there's some kind of like positivity
hmm?
result.
I have so totally non-negative means like the all the minors are
Yeah, yeah.
non-negative. Where are those? I'm not entirely sure. There are probably people who have. I mean, are they? You could probably check some of the minors.
Oh, I guess
Uh,
not if you look at the lower right corner.
yeah, like this one
Or wait,
also has
no.
1, 1, 2, 1,
Mm,
so that's negative, right?
yeah, yeah.
Yeah.
Okay, cool. Never mind.
Damn. Like, it's just a bad matrix, I guess.
Can I ask a non-mathematical question?
Uh-huh.
How did you make your slides? What software do you use?
It's PowerPoint.
PowerPoint. Okay, nice. I've been using Keynote, but it doesn't have the right fonts. I like your fonts.
Mm, yeah. Uh, I on my Windows laptop have a whole folder of fonts. Uh, we should definitely talk about fonts after this.
Okay, will do.
Mm. All right, let's thank Aditya one more time, and we'll go ahead and stop the recording.